Okay, so continuing our discussion of the Wiener process, and we did mention that in the Wiener process what were the assumptions, and at the fag end I did also mention that the generalized Wiener process will be utilized, and I did mention that what are the terms which can be included. So, let us continue the discussion on the general Wiener process. So, generalized Wiener process for a variable x, that means z or x whatever, these are different variables I am trying to utilize or different symbol I am trying to utilize, but conceptually that is the same, can be defined in terms of dz, which is the general very simple Wiener process. So, now here a generalized Wiener process will have terms dz was basically delta z, which you have already considered, which is a simple Wiener process. Now, that would have basically two terms. The rate of change of dx would basically be consisting of two parts. One is a constant multiplied by the simple Wiener process plus a constant multiplied by the rate of change of time. Now, just before I proceed, these values of a or these values of b which you have taken, in this case they are simply constant. It could have been that rather than a and b, we could have had a, which basically a function of time into dt, plus b, which is a function of time into dz. So, we are not going to make our life complicated, but we will continue our discussion, where dx, which is a generalized Wiener process, is now a function of two terms. One is delta t multiplied by a constant, and another is the simple Wiener process multiplied by the constant. So, now what does these two terms on the right hand side mean? The first term, which is a into delta t, implies that x has an expected drift rate of a. Now, why I am saying an expected drift rate? Now, if you take dt down, so what you will have? You will dx dt is equal to a. So, what you are trying to find out is the rate of change of x function with respect to time is basically constant a, that is why it is known as a drift rate, expected drift rate in the long run. So, it is the expected drift rate of a per unit time, that dt is basically per unit time. If b into dz is not there, then we would basically have the equation which is x is equal to x 0 plus at. So, x 0 is basically a starting value. So, if I want to find out dx, and we are considering that the first value of the difference in the first instant is delta x 1, it will basically be x 1 minus x 0 is equal to delta x 1, and will basically proceed. So, if you want to find out the second one, it will be basically x 2 minus x 1 is equal to delta x 2. If you want to find out the third one, it will be x 3 minus x 2 is equal to delta x 3. So, we will have x equal to x 0 plus at, where x 0 is the value of x at time t is equal to 0, which would be known to us. As of today, we know the value. While the second term, which is b into dz, implies the variability. So, now when I want to find out the expected value and the variability of x or delta x, it would basically have two terms. If I take the expected value, it would be given with some function of a, where a is basically the expected drift rate, while the amount of noise would basically be given by b, such that using that amount of noise b, which is external forces, we can find external effect, we can find out what is the variability of the whole generalized Wiener process. Now, if you notice, I have written down this equation somewhere, where given x equal to x 0 plus at, I can basically go iteratively and find out this value. So, that should, will come out later, and that should give you a hint that given the starting value, how you can simulate. Now, you may be thinking that, so simulation, would it give us a whole lot of information? The answer is yes, because if you are able to simulate it infinite set of times, then we will be able to find out that in which direction the prices would move. That would give you a intuitive feel that how the whole process works. Thus, we would have that if you consider the generalized Wiener process. So, initially you definitely had a into delta t, then in the second term you had b into delta z. So, now this is delta z, which has been replaced by epsilon into square root of delta t, where epsilon is 0 1. So, if we continue this, and if we try to find out the expected value of x would be a into delta t, where this is the drift rate per unit time. Variance would be given by b square into delta t. Obviously, it would be a square, because if you remember the formula initially which we have done, it basically x minus E x into f of x dx. So, this is the square term which is basically being implied by b square. The difference in the expected value of the expected value difference what we have is basically x t minus x 0 would be given again by this drift, but remember one thing, this was delta t and this is t, and also remember this was true, which is the number of such drifts which you have small deltas, and if you count n number of them, that would give you the overall time length. Again I am drawing, these are the deltas, these are the deltas, there are n number of them, add up all of them, you get the capital T. And again the variance of the difference of x capital T and x 0 would be given by the same formula, which is b square, but here rather than delta it would be capital T, again capital T is equal to n into delta t. Now, I am trying to basically draw, given this is, if you remember, this is the Wiener process, simple Wiener process where the expected value was 0. So, this is the Wiener process, it is going like this. So, the average value is always 0, and if I consider the generalized Wiener process with the drift and the white noise, then you will see this would be given by the rate of change of the drift. So, if you find out the tan of theta, that would have a functional value which is related to A is here. So, this is what is being given, dx equal to a plus delta t, and the variability would be given by this term, where dz I have to basically express as epsilon into delta t. So, utilizing this, you can formulate very simply the generalized Wiener process. A stock price starts as 40 and has a probability distribution given by normal distribution of 40 as mean value, 100 as the variance at the end of the year. If you assume the stock process is Markov process with no drift, that means A is not 0, then the process would be given by S, which is the spot price or the stock price is basically x which we are discussing. So, this is rather than dx, it could have been dx also. So, this is now we are trying to utilize the symbol in order to make our understanding simple. So, ds is equal to, this is 10 would basically be the factor which you have already seen. So, if you see the formula, what you had is a into dt plus b into, say for example, dz. So, this is the value of b which is 10. So, ds is equal to 10 into dz. If the stock price was expected to grow by 8 on an average during the year, so that the year end distribution would be normal distribution with 48 as the mean and 100 basically as the variance. Now, you are seeing that why variance is not changing, because the value of okay, I will come to that, just first let me finish it. So, that the year end distribution is given by n, 48 is the mean value, 100 is the variance, the process would now be dx is basically dx or ds, whatever you are considering. This is the term which is the first term, which is a into delta t, and this is the second term which is basically b into delta z. So, now depending on how the process is fluctuating, you can simply do like this. This I am giving in a rudimentary, very qualitative field. If you see the equation, the left hand side is ds. So, you will ask yourself, what is the question, what is ds? So, ds, if you remember, is the difference in the stock price. So, now the next question would be, how do you find it? The answer is very simple. You know S0, which is the stock price of today. So, note it down. So, let us note down S0. Now, your next question is that what is 8? 8, if you remember, is the average rate, which if you remember, we have been discussing the rate of change of the interest rate, which basically the 8, that so called RF, if the stock was exactly equal to the risk free interest rate. There could be instances where the stock was better than risk free interest rate, then that interest rate would be greater than 8. And what is delta dt? dt is basically simply again the difference in the time. So, time as of now t is equal to 0, at the next moment t would be 1, next to next that would be t is equal to 2, and so on and so forth. So, when I am measuring time t is 1, 2, 3, 4, correspondingly S, which was S0 at time t is equal to 0, will keep changing to S1, S2, S3, S4. So, the moment I mention that, it would be immediately become clear to you that ds or delta S would be now this S1 minus S0, which is the first difference, S2 minus S1, which is the second difference, S3 minus S2, which is the third difference, and so on and so forth. Correspondingly, what is the difference in the time? It will be 1 minus 0. 1 is not the numeric one, is the time unit. 1 minus 0 is the first difference in the time, 2 minus 1 is the second difference of time, 3 minus 2 is the third difference of time, and so on and so forth. So, we have been able to understand the first term on the left hand side and the first term on the right hand side. Now, what remains is to understand the second term on the right hand side, which is 10 into delta z. So, now 10 was basically given as the white noise, which we will also calculate from the external sources, as we did for 8, which is the rate of change of the stock price from the historical data. Now, we will ask what was dz. We already know it is a simple Wiener process. What is the equation? Is epsilon into square root of delta t. So, now you will ask yourself, where do we find out delta t? We have just found it out. Delta t for the first unit was 1 minus 0, 2 minus 1 is the second unit of time difference, 3 minus 2 is the third unit time difference. So, you already have that. Now, the next question to be answered is, and the last step is that what are the inputs was, what is epsilon? Epsilon we already know is normal distribution. So, given the picture of the whole equation, delta s are the difference of the stock prices, and you know what is S0 when you start. On the right hand side, you know 8 from the historical data, you know 10 from the historical data, and you also know what is the time difference, 1 minus 0, 2 minus 1, 3 minus 2, so on and so forth. You also know a normal distribution with a 0 mean and 1 variance or a standard deviation, and you also know delta t, square root of delta t, which will be used in the Wiener process. So, what you need to do is that you need to do simulate it very simply. How you do that? Consider the time difference is now, say for example, delta t is 1. So, based on that fact, if delta t is 1, you randomly generate one standard normal deviate from the normal distribution. So, on the right hand side, you have 10 into that normal standard deviate value, which you have generated the first instant, multiplied by the time difference square root of that, which was delta t square root. So, it would definitely you will have it. So, if the time difference was 1, it would be 10 into, say for example, standard normal deviate is coming out to be, say for example, 0.292, it would be 10 into 0.292 into square root of 1. So, this is the second term on the right hand side. What is the first term on the right hand side? You already have 8, 8 would be multiplied by 1. And what was on the left hand side? It was basically S1 minus S0. You already know S0. So, take S0 onto the right hand side. So, everything on the right hand side is now known. Now, you need to calculate and find out S1. So, once S1 is find out, again you will basically generate the data for the standard normal deviate, get the data for the time difference, and basically try to generate S2. So, you will go doing like this, but remember one fact, this is just a sample set of the realized value. If you do the experiment again, it is highly likely that all the values you will generate would be different, which is fine. So, what you are trying to do is that if you keep generating all of them infinite number of times, like if you keep tossing a coin infinite number of times, the average value which you get for a head, average value you get for a tail, or if you keep rolling a dice for an infinite number of times, the probability of getting number 1, probability of getting number 2, or so on and so forth is 1/6. In the same way, as you keep generating that, you will get the average values, which is what we have just discussed in the last 2 slides. That means, the average values, expected value of in the bracket z t minus z0 is 0, or expected value or the average value of x t minus x0 is 0. So, if you are able to do it infinite number of times, you will find out the values which were stated are actually what they are going to come in the simulation run. Now, let us basically proceed to the Ito's lemma is a type of a generalized Wiener process. In a Ito's lemma, the process, the drift rate and the variance rate are now functions of time. So, if you remember in 3 or 4 slides before, I had scratched and told you fleetingly that A can be a function of time, B can be a function of time, which is the average rate can depend on time, and the white noise score is also dependent on time. So, this is what Ito's lemma is going to consider here. Now, you will have dx, which is the difference between x. Initially, it was a into dt, now it is a into x into dt. So, x is basically is where you are. So, the drift rate would depend on 2 things, where you are and what is the time difference based on which from where you have come. And the second term was what? B into dz, dz remains as it is as the simple Wiener process, but now B is basically dependent on two functions, which is basically x where you are and the time difference from where you have started, where you are standing. So, the discrete time equivalent would be again given by this, which is delta x is equal to a function of x into t into delta t. So, this is the equation, and b x in which is function of x into t remains as it is, and the Wiener process is now again expressed as an epsilon, which is normal distributed with n 0 1, which is normal distribution of 0 mean and 1 variance or a standard deviation, and delta t square root. So, again you will basically generate this data according to the same concept, but remembering that now A and B are not constant, but dependent on two things, time and the place where the overall variable is being measured. Why a generalized Wiener process is not appropriate for stocks? For a stock price, we cannot conjecture that its expected percentage change in a short period of time remains constant, not its expected absolute change in the short period of time. So, what we are saying is that depending on the value, that the rate and the volatility would change, but the rate of change and the volatility change happens in such a way that they are not exact replicas of the generalized Wiener process or the concept of Utah's lemma, but the conceptual framework based on which we are trying to understand would remain the same. So, this would give you a much better understanding how the stock market or the stock prices fluctuate. We can also conjecture that our uncertainty as the size of the future stock price movement is proportional to the level of stock prices. So, where we are today would basically have an effect on the volatility later on. So, if the stock price is 10 and another instance for the same stock, the stock price is 100, then the variability and the expected value would also depend on the values of 10 and 100 from where we have started. Leave aside the time, time is also a factor, but now it is being dictated at what value we started there. So, if the values are very low or if the values are very high, it will have a positive or a negative effect on the overall expected value and the variance. So, now Ito's process for a very simple stock market. So, if you remember that delta S or delta X, if we consider delta x, it had two terms, A into delta t plus B into delta z. Now, if you basically expand this with respect to delta s with this change of the stock price, this is exactly what you have. So, this is basically A and this is delta t what you have, and the second term is not being considered for the time being. So, as delta t changes to 0 and after integrating, we can easily prove this is true, which is exactly what we have done in few slides before and we have been discussing time and again, which means the spot price S t is equal to S 0 into the e to the power R t. So, we have been mentioning R as the risk free interest rate, which was fine for our calculation, but what should be remembered that the S t, which is the specific spot price of a particular stock, would depend not on the risk free interest rate, but we would depend on the mean value of the rate of change of that particular stock prices. So, now we are trying to replace R or R suffix f with the corresponding rate of change or the continuous compounding interest rate of that particular stock. So, it can be positive or negative depending on whether the prices are increasing or decreasing. But the question is that what has happened to the volatility? As I mentioned, we are only considering the first part, the second part has been missed. So, if we continue considering the second part, so here S was there, now bring S downwards. So, what you will have delta S by S, which is here, ds or deltas are the time difference what you are considering. Now, here it will be, if S goes, it will be mu into delta t, which is here, where mu is the rate of change of the mean value increase, which is basically A. And the next term was what? It was B into delta Z. So, this is what we are considering. B is the, if you consider it was basically the white noise. So, this is what is standard deviation of the stock into a simple Wiener process. Now, if you consider this whole equation is a partial differentiation equation, where on the left hand side we have the ratio of rate of change of the stock prices divided by the stock prices as of now, S is equal to two terms. First is the mean rate, which is mu into delta t is the time, and mu is the rate of change of the functional form of the stock prices, which is happening on a daily or on unit time basis,
and the second term is basically consists of two things, which is the white noise, which is now being replaced by the sigma, which is the volatility or the standard deviation multiplied by dz, which is the simple Wiener process. This model is sometimes known as the geometric Brownian motion. Brownian motion, if you remember Robert Brown, who was basically studying the pollen grains, and as light fell he saw them vibrating very randomly. So, based on that the concept of geometric Brownian motion came. So, now if you remember and if you can recollect, we have been able to break down the overall Ito's lemma or Wiener's process, whatever mathematical proof has been, into two simple concepts. One is the average rate, which is mu into delta t, and is the volatility, which is the sigma into dz, which is the Wiener process. So, now again the question, how we will calculate, we will try to answer that in the next class. Thank you.